I don't know if whoever taught you Java in the previous class showed you the API documentation. This is large and confusing, but it is exhaustive. If there's any technical detail about the Java framework that you possibly want to know, it is probably here. So, for instance, if you're looking for, let's see, if you want to see something on system.out, we can eventually find the S section. Come on. Like I said, exhaustive. Exhausting, too. System. And there's out. There's also a link to the mechanics of the printf method. So there's system.out.println. There's also system.out.printf. I like system.out.printf. I also come from a C background, and printf is the way to print stuff to the screen in C. The book in the beginning of chapter 1, or toward the end of chapter 1, but in chapter 1, talks about printf briefly on page 14. So the author, also a C programmer, the author of this book is a CS professor up at Boulder, has collaborated with Walter Savage, who wrote the book that I'm using for 1150 this summer. Walter Savage is one of the guys who wrote the textbooks, the modern textbooks for C and C++. So I assume that Michael Mann, the author of this textbook, also a fairly strong background in C, and that's why he likes printf. So even if you don't know, even if you don't care to use printf, it's a good thing to be familiar with, so that in his examples, if he uses printf, you understand what's going on. And the basic idea of chapter 1 is the phases of software development. Can anyone tell me what top-down design or development is? I know both Dion and George know, because I told them in their respective classes last semester. Dion, would you like to explain what top-down development is? I know, the first day, and I'm putting you on the spot. George, how about you? You want to look at your notes. Anyone else familiar with top-down programming, design, development? Keyword being top-down. So the idea behind top-down programming is that you start with a large problem, and it's kind of big and overwhelming. So you break it up into smaller problems, and sometimes even they are kind of big and overwhelming. So you break them down into even smaller problems. And each one of those, hopefully, is manageable. You solve each of the smaller problems, and then you build them together to solve the larger problem. And Java has a couple different ways that it provides to make this easier for you. You have classes where you can divide up chunks of functionality following the object-oriented programming principles, treating concepts as things that have attributes and operations. And it also has methods, so you can break up the pieces of execution into individual chunks of code that can then be reused in different situations. So for instance, if we want to write something to the screen, we don't have to write all the mechanics of writing something to the screen every time we want to do that. We just call a method, system.out.println, and that handles everything pertaining to taking what we give it and printing it to the screen. That also means that there's separation of responsibilities. As long as something says it does a particular operation, we trust it. Which, if you have trust issues, Java is probably not a good language to start with, because it's very much in the encapsulation mode. Something says it's going to do X, you expect that it's going to do X. You don't want to worry about whether or not X actually happened. So it's possible that system.out.println could do something completely different, but we're just going to trust that it prints stuff to the screen. The first section of Chapter 1 talks about kind of more software engineering oriented concepts than I'm really worried about in this class. I run a software company, so I am very interested in software engineering, and software engineering is one of my favorite topics in computer science. We're not going to worry about it too much. The basic idea that's important to know for this class is figure out what you want to do first, then write the code to do it. Don't just sit down and start writing code immediately. Chapter 1 also talks about preconditions and postconditions. And these are very important when it comes to testing and debugging your code, and especially with data structures. Data structures are more complicated sets of data that are managed in specific ways, providing a very specific interface so that you can manage it in a way that makes sense in the given context. In 1150, or whatever intro Java course you took, the most complex data structure you had was the array. And that had certain limitations. For instance, if you wanted to, you had an array that could store 10 items, you wanted to store more than 10 items in it, you had to do something else. You had to think about how you were going to change the array to store more items in it. Data structures abstract that away and provide some piece of code that just handles that. If we add a new item to our data structure and it doesn't have room to fit that data structure, we assume it's going to do something sensible, allocate more space, get a bigger array. But it will handle that. So we have separation of concern as well. Preconditions and postconditions come into the picture in that when we enter a method, we make certain assumptions about the state of the object that the method is a part of, the instance that the method is a part of, the arguments that are passed into it. We might assume that an argument is not null. That's usually a good assumption to make and be explicit about. And postconditions are also known as side effects, byproducts, side effects, that sort of thing. What we've changed in this object or in other parts of our program that aren't directly part of either the arguments or the return value. So in addition to just having inputs, outputs, and something that does something in the middle, we have preconditions, which refer to the state of everything before we start doing the method body, and postconditions, how that's changed when we exit the method body. Arguments and return values are neither preconditions nor postconditions. And the comment block that's mentioned in the syllabus specifically mentions each of those. So parameters / arguments, return value, preconditions, and postconditions. Because they are different things, And when we're dealing with complicated data structures, it's very important to be explicit about these sorts of things. I don't know if anyone got into Javadoc in their previous Java experiences. You don't have to use Javadoc to document your methods and classes. I'm not going to run Javadoc on your programs and expect it to show this pretty stuff. Just comments, how you're familiar and used to writing comments is fine. Then a lot of chapter 1 is programming tips, things the author thinks are good things to do. It's more personal preference than actually this is how a data structure works. Programmers have conventions, and unfortunately lots of different programmers have lots of different conventions. But I definitely recommend picking a convention and sticking to it. Makes your programs more readable, means that it's easier for other people to work with your programs, run them, that sort of thing. The second section of Chapter 1 talks about runtime analysis. And this class is not particularly concerned with runtime analysis. While it is data structures and algorithms, we're not going to emphasize the algorithms part in its own right too much. The only algorithms we'll really talk about is in terms of how they apply to the data structures that we're using. The emphasis in this class is definitely on the data structures. There's another class that if you're a CS major, you'll eventually have to take design and analysis of algorithms or something along those lines. That's where you'll really get into algorithmic complexity, runtime analysis, and specifically algorithms that assume that you have data structures. That's more of a math-oriented course. In this course, our main concern with runtime analysis is the relative speed between algorithms, operations. So if a method that has a very specific number of statements that all get executed once is said to run in constant time. It's always going to take the same amount of time regardless of how many elements are in a data structure, elements that are in an array, objects that are created in all of Java space. If the method is dependent on the number of elements in a given set, it does a fixed number of operations for each element in that set. It's said to have a runtime complexity of n. Doesn't matter how many operations are done on those n elements, the computational complexity is still n. If you have a double for loop, for instance, then you start getting multiplications. Because say you have, did anyone do any sorting algorithms in the previous Java courses? George is the only one. Okay. If you were to iterate through a list, and then each time you iterate through the list again. So now you have a certain set of operations that you do for every element in the list. That's n. And then the operation that you're doing for every element in that list is iterating through every element in that list. So that's another n. So you end up with n times n, or n squared. And there are more complex formulations of runtime analysis. But for the most part, what we'll see is either it'll run in n time, n squared time, or log n time. And we won't see log n time until the second half of the summer semester, when we start talking about trees. And I'll explain how that comes about when we get there. So now we get to testing and debugging. I'm sure you're already familiar with some method of doing this. You have to, in very early Java, you kind of have to create your own method of testing and debugging. And it mainly comes about when you get, in Dr. Java, it's an error with an ugly yellow background, or it crashes with something in ugly red text. Either one is bad, and either one means there's a bug in your program, mainly the red one. That's a runtime error. That means you gave it input that it didn't understand. It explodes. And there are very formalized ways of testing and debugging programs, but they really boil down to finding boundary cases, which means the specific values that you're testing against to choose which code path to follow, for instance. The things that could potentially break your program. 0 is usually a good one. Most of the time when we write algorithms, we think of cases where, for instance, our arrays have some length. We have an array of 5 elements, and then when we give it an array of 0 elements, things break horribly. So that's always a good boundary case, always a good test case. And that's the sort of thing that when you write your main program to test a data structure, you might want to test those boundary cases to make sure it's going to work. When I'm grading programs, I don't go out of my way to break your program. Again, all of the programs for this class will be in a very specific situation in terms of the interpreter for this instruction language. Every program will be a well-formed instruction language program. So you don't have to worry about handling, if I were to feed it an instruction language program that was wrong in some way. Every program that I give you for these particular assignments should run on a fully built simulator. And in order to simplify it, the language that you're writing an interpreter for does not actually exist. So unfortunately, there's no reference implementation. So chapter 1 is a lot of I would say irrelevant stuff. It's not specific to data structures. It's kind of the general introduction to this is what you need to know before you jump into data structures. So, are there any questions on that? Would it be helpful if I gave a quick whirlwind tour refresher of how to write Java? Okay. So I will pull up Dr. Java. I will try anyway. So we can start very simple and whoa. That is the simplest possible Java program you could write that will run. And we'll start with the 3 basic functions that any programming language or computer needs in order to solve every problem that is computable, which is sequence, selection, and iteration. So
sequence
It's a pretty straightforward program, right? Does anyone see anything that they're unfamiliar with, that they have questions with, or is this all pretty familiar to everybody? Who wants to tell me what this program will do? Yes. Slight difference between Java on my machine and Java on these machines that we might run into when we start getting into a topic called generics. I'm using an older version of Java because OS 10 ships with an older version of Java. These machines all have Java 1.7 on them. I only have Java 1.6. That should change sometime in July when Mountain Lion is released. $19 on the Mac App Store. $20, $19.99. So at that point, I will have to go get an Oracle version of Java, and then I'll be at 1.7 as well. So I compiled it, and I can run this program. And let's add 8 and 7, which should give me 15. Any questions on that? Yes. So Commenting is one of those things where there are multiple different conventions. Some people expect every single line to be commented. Some people expect no lines to be commented. What I suggest people do and what I actually do are two completely different things. I'll be honest about that right now. I'm absolutely terrible at commenting. And most of the time when I'm writing stuff on the screen, mostly for sake of time, I won't comment because I'll be talking and explaining what I'm doing as I go. For your own programs, if you look at the syllabus, the very last thing in a description of a method is a description of how the method operates. And I say that this should not be a line-by-line narration of the statements of the method, but a bird's-eye view of the concepts that it implements. So in this case, something like accepts two numbers from input and prints out their sum would be more than sufficient. Because if you start commenting every line, you get ridiculous things like that. That doesn't tell me anything about the statement. I can see that just by looking at the statement. If I don't know Java, maybe that would be helpful. But if I'm looking at this code, the likelihood is that whoever's looking at the code knows Java. So that comment really doesn't do anything except take up your time.
Will there be like reduction in points if you don't?
If you don't comment at all, I will take off points. If you don't adequately describe what a method does, but I can figure out what it does, that's the communication has happened. That's really the point of comments. If you forget to comment a method that's like an add method, it's very simple, doesn't do a whole lot. It's pretty easy to figure out what it does. Not a big deal. And as a teacher, sitting down and grading based on 100 points, once you start grading programs on that, 100 points isn't a whole lot. So if I started taking off points based on every missed comment, that would skew the grade unfairly in favor of people who were very meticulous about comments. So some comments is better than no comments. No comments will get a reduction in points. Don't get ridiculous with the comments. Yes?
Have that be A?
Did I?
Unlike A, you have a plus 3, but you adding A.
I was thinking for the computer. The more you write programs, the less you trust computers. So occasionally I'll do things like that. But thank you for catching that. Mm-hmm. And that's a very good example of a bug that if it mattered, and if I ended up using A as the input to something and hard-coded a 3 instead of using an A, that's one of the most irritating errors to encounter and one of the hardest to find. Because you looking at your code know that makes sense. Yes, A is 3, so 3 should go there. When the program runs, 3 is going to end up there. So you don't see it. So with programming, obviously in a class situation this is a little different, but in programming it's just like in English. It's a good idea to let someone else look over your program and make sure you didn't do anything stupid. Just like it's good to have someone else proofread your English papers. As far as in the class setting, the official college policy is that hopefully nobody cares when they hear this on the video recording. The official college policy is that collaboration is incorrect, is academic dishonesty, and that policy works very well. Those policies were written before computer science came about. So it works very well for English. If you take someone else's work and paraphrase it and don't give them credit, that's wrong. That's academic dishonesty. Computer programs are different. Computers have a very strict set of things that they will accept to solve a problem. And while there are multiple different ways to solve a particular problem, if two people are solving a problem the exact same way, the likelihood that they have statements that very closely resemble each other is very high. That doesn't make it wrong. In addition, coding in the real world is collaborative. Very frequently, me and the other developers at my company are standing over each other's shoulders looking at code and solving the problem together. If that helps you, if you are stuck on a particular piece of the assignment and want to ask someone else, go right ahead. There's nothing wrong with that. When it comes to submitting your homework, it should be your own work, though. So sharing of concepts and ideas is perfectly acceptable. Sharing code and copying and pasting each other's code, not acceptable. It's especially easy to find if people have copied and pasted the exact same wrong answer for something. So if you're going to copy and paste someone's code, not that I recommend it, but if you're going to copy and paste someone's code, make sure it's right. Which kind of defeats the purpose. If you're going to make sure it's right, you might as well write it anyway, because that means you still understand what's going on. And my grading style is very much focused on demonstrating that you understood the concepts. So if you had a mistake like that, accidentally put 3 instead of A, not a big deal. You understand what that statement was supposed to print out. I'll let that slide. All right, so sequence. Let's do selection. Another thing you might notice, I very much follow I guess it's the C# convention. It is also a C convention as far as where the curly brace goes. And my business partner gets very frustrated with me about this all the time because he's on the other side of the fence. I generally put the curly brace on the next line. The Java convention is to put it on the same line separated by a space. I recommend following the Java convention. Again, that doesn't mean that I will always follow the Java convention. It's very hard to break old habits. Simple if statement demonstrating selection. And finally, iteration. So there is an implementation of a while loop and a for loop they're essentially analogs of each other. There's also an implementation of a for loop that iterates over objects in CS1150. The only thing that they iterate over is an array. In this class, we'll use them for more than just arrays, and we'll see that in the next couple of classes. So here's the first type, for loop. So there's simple iteration. Let's go down here. Let's make a constant. I'll spare you the additional digits of e and pi. Let's see. Those aren't transcendentals. Sure. They're all the ones I can think of. Has anyone not seen that formulation of the for loop? Okay. The basic structure of this for loop, this was new in Java 1.5, I believe. This is also referred to as a for each loop, even though the word each doesn't appear anywhere here. The problem it was trying to solve was that other programming languages had a formulation of a for loop that would do some set of statements for every element in some set of elements, some set of things. So the basic formulation is the piece to the right side of the colon is something that is a set of things. In later chapters, we'll actually learn it is something that implements the iterable interface, basically meaning that things can be iterated over. You can get each element in turn and do something to it. And on the left side of the colon, it's basically just variable declaration. And you can read this as for double D in irrationals. So for each element in irrationals, the variable D will take the value of that element in turn. So irrationals has 3 elements in it. This loop will execute 3 times. Each time it will have the next element of irrationals and print it out. So if we compile and I knew I was missing something. So that's that yellow error, that big scary yellow error. And it prints out the values of those numbers. I can make it print out a big scary red error as well. And this one will be contrived. Trust me, that doesn't work. You can't have a scanner on nothing. And in order to demonstrate this, I do have to perform a typecast, which should be something that's familiar to everybody. Is anyone not familiar with typecasting? Okay, the basic idea behind typecasting is that we have something that's of one type and we need it to be another type. For instance, we're passing into a method that accepts a variable of some type. But what we have is the variable itself is declared as being a supertype, or some different type. And we basically need to coerce it into being the type that we want. And the way to do that is to put the destination type in parentheses next to the value that we want to convert to that type. And if you didn't get to inheritance and multiple classes and the big parts of object-oriented programming, you probably have only seen it with ints and doubles. So you can convert an int to a double without using a typecast because a double can represent more numbers than an int can. But if you want to convert a double to an int, you need a typecast. So that it basically loses the fractional value and turns it into an integer. And it will crash hardly. So this is something called an exception, which may or may not have been covered in your previous class. We'll mention exceptions and how to deal with them in this class as they come up. Basically, Java encountered something that it didn't know how to handle and exploded. Java is a very violent language. And the appendices in this book provide a decent coverage of some relatively simple Java concepts. Appendix C specifically talks about throwing and catching Java exceptions. I guarantee whatever book you used for your previous Java course has a section on exceptions in it, whether or not whoever was teaching it covered it. I know that the Y. Daniel Yang book does have a chapter on exceptions. Not a good one, but it talks about exceptions. Yes, George.
If you go on top of the building, please.
Yes.
To line. Wait, line 5.
Okay.
Why did you use a public stack? Why didn't you just do the final array declaration after the public stack board name?
I wanted to demonstrate the use of a constant. The book mentions using constants in the middle of chapter 1.
Right. I thought you were still going to use it like that.
You can. I wanted to demonstrate using a constant. That's really the only reason.
Is there a difference using it as a public static though? Because
If it's inside the method, you can't determine whether it's static or not.
right.
And inside the method, you can't specify public or not. You also can't specify final inside the method. Yes, you can, but it's not really a constant. In order to be a constant, it needs to have two things. It needs to be global, accessible everywhere, and have only one copy. And it needs to be set to a value once and then never changed. That's the main definition of constant. So if you have final inside a method, it is constant in the sense that it will never change. But it is not globally accessible. So math.py and math.e are good examples of true constants,
Which are good.
which are global. When decisions come up like that, the path you choose is really quite arbitrary. If the requirements of the particular program don't dictate one way or the other, it's really up to you. And that's more of that kind of self-taught software engineering. Let's see, what haven't I talked about? Array, sequence selection, iteration, arrays, exceptions. Does anybody have any particular things that they're shaking on in Java? In that case, we can take a 10-minute break, and when we reconvene, I'll talk about the homework that's not being technically assigned until Thursday.